Welcome to the third part of the tutorial T12 titled Underdetermined Wideband DOA Estimation and Target Localization. So this is section 5. So we will finish all the remaining sections of this tutorial in this part. So section 5 is about underdetermined wideband DOA estimation, exploiting higher order statistics. Section 6 is about underdetermined wideband target localization. Okay, and section 7, that's the summary. So first, for section 5, we have 4 subsections. One is the signal model, and then the wideband DOA estimation employing this group sparsity, and then wideband DOA estimation with focusing. Okay, and then I will provide some simulation results for this section. So far, the covariance concept introduced in this tutorial is only based on the second order statistics. So to further increase the DOFs of the system, so we can employ this higher order statistics, such as its cumulants. Okay, these kind of methods have been developed as part of this 2Q order difference covariance concept. So the typical value of this Q is 2, so that will be the 4th order difference covariance. And for this cumulative based, it has the additional advantage of improved robustness against strong background Gaussian noise, because for cumulants, normally assume the source signals, they are non-Gaussian, and then the noise is Gaussian. So if you calculate cumulants, then the cumulative noise will be 0. So then you have removed the effect of noise. Okay, and you can also have this 4th order difference covariance not through this cumulants, this kind of non-Gaussian assumption. So the signal could be Gaussian. So, but we make another assumption, this non-stationarity. So the 4th order difference covariance based estimation method for quasi-stationary sources, it was proposed in this reference 35, and the source signals can be either Gaussian or non-Gaussian. So we just exploit this non-stationarity of the signal. So there's different ways of achieve this 4th order difference covariance. Okay, so in general, for this 2Q order difference covariance, so the big O of this n to the power 2Q DOFs can be provided with only n physical sensors. So in this part, we briefly review the underdetermined wideband DOA estimation methods proposed in reference 44 for non-Gaussian signals. Okay. First, so consider this linear array of these n sensors and the locations, so alpha 0D, alpha 1D, and so on. And D is a unit spacing. And again, we assume so K incident signals, so coming to the array. And then after sampling with the frequency Fs, and we can apply this L point DFT, so split the data into blocks. Each block has a size of big L, then you can apply DFT, L point DFT to this each block, and then you obtain this DFT domain, this signal model, right? We have been familiar with this already, given the previous section, so we have used this several times. Okay, so this is the P is the block index, L is the frequency bin index. So this is the steering vector, a steering matrix of the array for this frequency bin L, okay, for this frequency. Okay, and here is the noise. And then we can define this 2Q order circular autocumulant of this source at this frequency L using this standard definition, okay, using this symbol to represent this cumulant of this, okay, it's cumulant. And then we can define this n to the power u, a mu times 1 vector. So this one basically is a connector product of mu vectors, okay, of this individual steering vector A, L, theta, K. And with this definition, then we can calculate this 2/q order circular cumulant of the received signal at frequency L, indexed by this mu, okay? And then it's given by this result. If you calculate this, then you can express this cumulant in terms of the cumulant of the source. And then times this. This is a difference, and this is a fourth order difference corollary, okay? So you can form this fourth order difference corollary using this part. And here is the noise part. And for Q, for fourth order, so Q equal to 2, then 2 minus 1 is 1, then delta 1 is 0. So this part will be 0, because for non-Gaussian, for Gaussian noise, for the fourth order, then this part will be 0. But for if Q equal to 1, so 1 minus 1 is 0, so here's 1, then you will have this noise part, okay? And then, so from this operation, okay, you can achieve this, okay, fourth order difference corollary. You can generate this virtual corollary, so fourth order, so 2/q order, okay. For Q equal to 2, then it will be fourth order. Basically, you can two of them sum together. This index is so alpha, like alpha nm, and the other one, so nm is m equal to 1, from 1 to q, and this m is from q plus 1 to q. So basically, two of them, you randomly choose two alpha values from this set, and then add them together, and also choose another pair, add them together, and then you take the difference. So you can find all those different values after this, so with this operation. And then you vectorize it, okay, as before. So you can vectorize this cumulant, okay. And after vectorization, you have this new, so virtual array model again, so very similar to the previous model. So you have this BL theta. This is the steering matrix, okay, steering matrix, and this is a virtual source signal. And here, this one is the vectorized version of the matrix for the noise part, for this part. So this identity matrix, you vectorize it. Certainly for Q equal to 2, this part will be 0, okay? And this BL theta K, so BL theta K, this steering vector, virtual steering vector for this fourth order is given by this, okay? So basically you have 4 components of this AL theta K, and you do this Kronecker product, okay? And then you have this, you can further, okay, simplify this, right, by combining this as before. So we're combining this noise part, merge this noise part into this, okay, generate a new steering matrix. So you have this new model. So add the noise part to this, form a new steering matrix, and add the noise part to the source signal. So you have a new source signal vector. And then you can create this search grid of this kg potential instant angles, right? This theta g0, 1, and until this big kg minus 1. So, and then we can construct the corresponding steering matrix, this is a big steering matrix. And then again, you add this noise part to this steering matrix and form this new steering matrix, add the noise part to the source vector, okay, to generate this new source vector, okay, and then you can have this again, so the similar formulation using the sparsity-based DOA estimation method. So you minimize this L1 norm of the source, and then subject to this, you have a construction error, so reconstruction error smaller than or equal to this epsilon. And we can extend this to multiple frequencies through the application of group sparsity straightforwardly as before. So this, we have this model here, then you can construct this block diagonal matrix, right? Remember that operation. So assume we have M, big M, smaller than or equal to L DFT frequency bands within the bandwidth of signals with the indexes described as LM, so M from 0 to big M minus 1. And then you form this block diagonal matrix, okay? So for each being, you take this one for different L, right? You take all the possible values of L within this range from 0 to big M minus 1, then you form this block diagonal matrix. And at the same time, you take all this vector ZL for different values of L, put them into a long vector. And at the same time, you can also put this into a long vector, okay? But before we do this, we can form this data matrix first. So we can form the data matrix first, and then we do the vectorization of this. At the same time, we calculate the 2-1 norm of this source vector, this new source matrix. Calculate L21 norm. We minimize that, right? So we minimize this L21 norm. So this is a row vector. This one is a row vector of this one, and then each row vector you calculate the L2 norm, put them into a new vector. So this is L21. This is a new vector, and then minimize this L1 norm. So this is the so-called L21 norm of this data matrix. And then subject to this reconstruction error. So here's Z tilde is, you put this data for different frequencies into this long vector. Also, you do the vectorization of this data matrix. Basically, you put all these vectors together to form a new long vector, okay? And this is typical method to have this, to achieve this group sparsity, okay? And the main drawback of this group sparsity-based method is this high computational complexity, right? Because this is a very big matrix. This is a very big matrix, right? And for complexity reduction, so we can use focusing, right? We can use focusing. So traditional focusing method constructs focusing matrices for the physical array based on the correlation matrix, provided that a preliminary estimate of DOAs is given. So you know roughly the DOA angles of the individual sources, and then you can do this focusing corresponding to those angles, okay? And so as a result, its performance is sensitive to the estimation error of the initial DOAs. So the preliminary DOA estimation results will have a big impact on the performance, on the final result. Here, so we apply focusing to the virtual array structure, okay? To the virtual array structure, we don't apply this to the correlation matrix, okay? We apply this focusing to the virtual array structure, and the search grid generated for sparse signal representation is utilized as an initial DOA estimate. So we don't need to find the preliminary DOA results for each source. We just use the grid points, the corresponding directions, use that as the preliminary result, and we do the focusing based on those set of angles. So as a result of this, so preliminary DOA estimates are no longer required due to the significantly large number of DOFs provided by the virtual array, because the virtual array has a much larger dimension. So when you calculate the focusing matrix, you can have a small focusing error, although you are doing focusing for the whole angle range of interest, okay? So we consider FR as the reference frequency and corresponding to this LR frequency bin. Then we use the focusing algorithm proposed in reference 45 and applied it to this virtual array structure in 77. So go back to here, okay? And then so the focusing matrix TL, so we use this this is the data, this is the steering matrix, right? And then it's over this whole grid. Okay, this is kg of them. So you apply, this is reference, the steering matrix at the reference point, and this is the steering matrix at frequency being L, and you apply this focusing matrix TL to this steering matrix at frequency being L, and you ideally, these two, they will be equal to each other, so you have a zero focusing error. So in this case, but it will not have this zero value. So you will minimize this this error, this focusing error. So the difference between the focused steering matrix and the reference steering matrix, you minimize this error, and subject to what? To this is basically orthogonal. Okay, we assume, so we want to have a focusing matrix TL which is orthogonal. The reason is for this is, okay, in this way, you will not, so for white noise, you still have white noise and you will not amplify it, okay? So that's the requirement for this focusing matrix. So it's orthogonal one, also giving you this minimum, this focusing error, okay? So minimize this subject to this constraint. And the solution is given by this VL times UHL, where the column vectors of this in this UL and VL are the left and right singular vectors of this matrix. Okay, so that's the solution to this problem. And then you can apply this focusing matrix for frequency being L. So for each this frequency being L, you apply the corresponding focusing matrix. So times the data ZL, then equal to, you have a new set of signals with YL equal to this focusing matrix times ZL, and ZL equal to this, and this one times this, you got this one. And here is white noise. So you only have one sample, okay? And here, so this is the noise part, and this is the this is a common steering matrix now. So this is the source data at this frequency L. And so after focusing, the same equivalent steering matrix, so this one is shared among all frequencies of interest. And then you can do the averaging. So by averaging the signal at each frequency being, a single wideband model can be obtained. So you do the averaging at all of them. So you got this a single model, okay, like the narrowband model now, like you have one single frequency, okay. And then for the single frequency model, you can apply the sparsity-based DOA estimation method directly, right? So we just minimize this R1 norm, and you can basically so subject to the reconstruction error smaller than or equal to this epsilon, and minimize this R1 norm. Okay. One important property that permits the development of this focusing method is that in this underlying 2k order different Corey, this UGLM terms have the same sign across all frequency bands, and as such, their summation leads to coherent signal combination for improved performance. So when you add them together, right, you add all of them together. So you need to make sure all the signals, so the source signals, okay, they have the same sign. So when you add them together, they will be added together coherently, right? So you need to prove this. So this property can be verified and proved with some assumptions. Okay, you can find the proof in this reference 44. So basically, all the signs of the signals, they are the same. So you add them together, so you can enhance it. Okay, that's this focusing method. Simulation results. Okay. Consider this example. So normalized frequencies of interest cover the range from 0.5 pi to pi, and reference frequency is in the middle of this band. Okay, so 0.75 pi, and we used a nested array with 5 sensors, and the precision set of the 5 sensors, the locations are given by this. So 1D, 2D, 4D, 8D, and 16D. And D is lambda R over 2. So we use lambda R, this reference frequency, as the unit spacing. Okay. And then we apply this 64-point DFT to the data. And the frequency band of interest covers 15 frequency bands. And so from 17 to 31. And there are key wideband sources with incident angles uniformly distributed between -60 to 60. And the search grade of these 721 angles with a step size of 0.25 degrees is generated from these -90 degrees to 90 degrees. This error bound is chosen to give the best result through the trial and error method in every simulation or experiment. Okay, so here is the number of entries in vectors matrices. Okay, so basically we compare the complexity, so with focusing and also group sparsity method. So group sparsity method has a higher complexity because the dimension is much larger than this focusing method. So you can see the number of this steering matrix, the number of parameters in this steering matrix. There's a big difference between these two. And you can see the running time. Okay, here is much smaller than this, right? So with focusing, you have a reduced computation time. So basically lower complexity. And here's some results, DOA estimation results. So for K equal to 12 and 0 dB, and the number of samples for each frequency is 10,000. And then there's have normalized spectrum. So estimation result, you can see both the group sparsity-based method and the focusing-based method, they can identify these 12 directions successfully, right? And then we compare this RMIC results. Okay, so you see the narrowband method. Okay, just use one frequency bin. Okay, it's not as good, but with focusing and with GS group sparsity, so you have a much better result. So, and for GS and focusing, you see these two, they have a similar performance. This RMSE result versus this dB, so from -5 dB to 20 dB. And for this, that's the part for this section 5, and then we move to this section 6. Is underdetermined target localization based on wideband arrays. And in this section, so we also have 4 sections, so signal model, and also we talk about this narrowband target localization, and then we talk about the wideband, and then I gave you some simulation results. Here, this underdetermined means, okay, because it's a distributed array system, so we have multiple subarrays. So when we say underdetermined here, it means, okay, for each subarray, the number of sensors is smaller or equal to the number of targets. Okay, so it's underdetermined in that sense. Okay. And for target localization, so different approaches have been proposed in the past for target localization with various sensor array networks, such as those based on received signal strength or time arrival or DOA. Okay, in this tutorial, in this part, we will focus on the DOA-based method. So for DOA-based or bearing-only localization, so DOAs are obtained at distributed platforms and then fused together to localize the target with reference to the distributed sensor array network. And this second step is normally achieved based on the maximum likelihood criteria. Okay. So this is a two-step method. You get the DOA or bearing first, and based on that, you find the location. Okay, that's the two-step method. So different from this two-step method, a two-dimensional group sparsity-based localization method is introduced in this part. So where the collected data at all receivers is exploited to identify the target location directly. So we find the location directly from the data, not through this two-step method, okay? And only the covariance matrix at each subarray instead of all the data samples is required for centralized processing. So you don't need to transmit a lot of data for this method, okay? Here, so we consider this distributed sensor array network. Okay, that's the layout. So you have M subarrays. So basically the platforms, M of them, 1, 2, and M. And you have targets, the K target, you have K targets. And that's the location for the K targets, okay? And then this phi 1K, phi 2K, you know, these are the angles relative to the Y axis, okay? That's the layout. And for each receiver, so each platform, each receiver, a linear subarray with LM sensors is employed. So for each, like this platform, you have a linear array here. This is a linear array, linear subarray, okay? The M subarray. And then this subarray has a rotation angle relative to this axis, this x-axis. Okay, this is a rotation angle relative to the x-axis. And also for each target, you have this angle theta mk. This is measured relative, okay, to this broadside of the array. So this is the broadside, this is a linear array. So this is the broadside of this, broadside direction of this linear array. So this theta mk is measured relative to this broadside. So these three angles, so this one, and this one, and this one, they are related by this. So basically, this angle theta mk equal to what? This plus this, because this angle is the same as this angle. So this angle plus this gives this angle. So that's why we have this relationship, okay? And for each platform, each subarray, right? We can have this discrete time. So we focus on this narrowband first, okay? The discrete time narrowband signal model, okay? It's given by this. So the I is time instant, so sampling each sample index, okay? So you have this steering matrix, and this is source signal, and for each so we have this SM. So for different platforms, the source signal will be different. We don't require the, you know, basically they come from the same target, but the signal can be different for different subarrays, okay? And here is a noise part. And then we calculate the standard operations. So we can calculate the covariance matrix. It's given by this. And this part, sigma squared, this M is the noise power, okay? And this is the covariance matrix of the source, okay? So starting from this model, because we have done quite some this sparsity-based DOA estimation. So starting from here, we can apply many existing sparsity-based DOA estimation methods to find DOAs, right? And then we can extend it to using group sparsity for direct target localization for both wideband and narrowband cases, okay? And in here, we just, as a representative example, we consider this co-array-based method, okay? Basically, so the sparsity-based method based on virtual sensors, right? Not the physical sensors. So we consider this co-array-based method, okay? To do this co-array-based method, then you do the vectorization, right? You vectorize this covariance matrix. So do the vectorization, Zm equal to this, vectorize this Rxm. And then you have this new signal model. You have one sample. This is a source vector. This is the equivalent to the virtual steering matrix. And this steering matrix is given by this, okay, virtual steering vectors. And then it's a Kronecker product of this individual, this physical steering vectors, okay? So that's a standard result. And here, from here, we can also form this again. So you can move this, merge this noise part to the steering vector for the source to generate a new steering matrix. And then this is the new source vector, right? That's the model. And then to do this sparsity-based estimation, so you can form this search grid of kg potential incident angles from, so for this set, so big kg of them. And then you can generate the corresponding steering matrix, right? And then you can put this so-called steering vector for this noise, okay, this one, into this steering matrix for the source to generate a new steering matrix, and then form a new source vector, including the noise part. And then you can do this optimization, so minimize the L1 norm of this source vector subject to this reconstruction error, right? Smaller than or equal to this epsilon. And then the kg elements of the column vector are the DOA estimation results, right? Now, that's a standard result for each subarray. You can do this DOA estimation using this method and find the directions. And then from these directions, you can find the location. That's a two-step approach, right? But here I say, okay, we can find the location directly. We don't find this angle first. We find the location directly, okay? So to do that, we just use this group sparsity concept. So apply this again, but apply this across the available subarrays, not across different frequencies, okay? That's the novel part of this method. So to do that, okay, first we consider this target. For each target located at this place, this location, and for each location, right, we have a unique incident angle, right? For each location, you can find the unique incident angle theta mk for each subarray. And first, you have so without loss of generality, we consider this a square area of interest. So the square area of interest in the Cartesian coordinate system is divided into kx times ky grades, with kx and ky being the number of grid points along the x-axis and the y-axis, respectively. Okay, so kx, ky, that's the total number of points you have along these two, x-axis and the y-axis. And then we use this xkx, yky to represent the location of the kx, ky search grade and the angle corresponding to this grade, and for the mth subarray can be obtained by this equation, okay? So for each location, you can find the corresponding angle measured from the broad side of the mth array. And so this part is just this phi mk. So basically we're using the result at the beginning. So for this angle, for any location, arbitrary location, right? Any point, whether there's a target or not, okay, any location, because you don't know where the target is. So for each location, you can have this theta mk using this relationship, okay? And this phi mk is the angle of this location relative to this y-axis, right? And then So this is given by this arctangent. Okay, this new function. We define this new function. Okay, basically, this is just if you know this coordinates of this location, then you can find that angle, right? That's a straightforward process. But mathematically, you need to consider this more complicated one because different signs of this location, okay, coordinates, okay. So you can find this given location, you can find this angle, right? So through this relationship. So as a result, so the formulation for DOA estimation can be used for estimating the location GXKXYKY by replacing theta MKG with this theta, so related to this KXKY in constructing this steering matrix. Now this KG equal to KX times KY. And we treat this as the parameters to be estimated, not theta anymore. We treat this as the parameters to be estimated. Okay. Since this XKX and YKY is common to all subarrays, and the source located at this G at this point will appear to come from the same location with respect to all subarrays. So for all subarrays, you share the same location, right? So we can apply this group sparsity concept to all subarrays source data, okay? So it's a group sparsity, right? So basically, if there's no target for that, for this location for one subarray, then there should be no target for all the subarrays for the same target location. So that's a group sparsity. So we apply this group sparsity concept across these different subarrays, okay, not across different frequencies, because here we still consider this narrowband model, okay. But now we have a, although it's narrowband, but we have this group sparsity problem, okay. So first we construct this block diagonal matrix, right, as before. So you have this formulation, right? You have this formulation here. So you can construct this block diagonal matrix, right? For each individual one, so block diagonal. And then you generated the source matrix, right? Source matrix, right? And then you can form this long vector for the observed signal, the virtual observed or observed virtual signal, okay, Z tilde, okay. And then this R is the long vector. So you do the vectorization, that's the corresponding. So put them in long vector, you have this relationship, right? And then you can minimize, because group sparsity across these different source vectors. So you can minimize the L21 norm of this. So you find the row vector, you calculate the L2 norm, put the L2 norm together into a new vector and minimize the L1 norm. So that's, so you minimize the L21 norm here, and subject to this reconstruction error smaller than or equal to this epsilon, this threshold. Okay. So that's the group sparsity based method for target localization for this narrowband case. Okay. Now for wideband, so we have been very familiar now with how to extend the narrowband case to the wideband one using the group sparsity concept. So for wideband underdetermined target localization, we can extend the formulation in the last slide here to multiple frequencies like before. So basically we add another layer of group sparsity, right? We add another layer of group sparsity. We can also apply the focusing technique, right, to different frequencies of each subarray and generate a narrowband equivalent virtual array model for each subarray at the chosen reference frequency. And then apply the group sparsity-based technique to combine the models for all subarrays for wideband target localization, right? So there's different choices for the wideband case. Because we have been familiar with that, so I will not repeat that process again, okay? is now quite straightforward, okay, based on this narrowband formulation. Okay. So one big advantage, main advantage of the group sparsity-based approach for direct target localization is that, okay, the different subarrays are not required to be synchronized, can work on different frequencies, and the statistical properties of the sources can be different for different subarrays. And sensor numbers, rotation angles, and corresponding source angles, source signals of different subarrays do not need to be the same, as long as they come from the same set of target locations. So that's advantage, because here, when you form this group sparsity, so this source, basically this SMI, right? This source signal for different subarrays can be different, right? So this M is dependent on the subarray. So you can have the same signal X or SI, or you can have different signals SMI. Okay, so here we have a general one, so SMI. So that's why that's big advantage. So different subarrays can receive different signals at different frequencies, and with different channel conditions. Okay, so that's a big advantage. You don't need to have a synchronized distributed array system. Okay, they don't need to be calibrated. Okay, so all these, okay, individually certainly they need to be calibrated, but not the whole distributed array system. Now some simulation results. Okay, although we do target localization, okay, here we just give you some extra simulation results like far field sources. So suppose the target is located in the far field of this distributed array system, then you have only angle to estimate in that case. And so frequency range of interest. So basically in the limit, you move the target to the further and further. So in the limit, the location, okay, you don't have location anymore, you have angle only. So frequency range of interest is from 7.5 kilohertz to 10 kilohertz. The reference frequency is 8.75. So is a center frequency for focusing. Okay, this is FR is used for focusing. Okay, in the simulations we have used the focusing method. Okay, and the normalized frequencies with the sampling frequency Fs is 20 kilohertz, cover the range from 0.75 pi to pi. We have 3 subarrays, U1, U2, and U3. That's the locations, coordinates. And the rotation angles, so 0 degrees, 6 degrees, and minus 21 degrees. We have a 4 sensor MRA, so minimal redundancy array, at locations, so 0D, 1D, 4D, 6D. So it's employed at each platform. And the D is given by lambda R over 2. Lambda R is the reference frequency. Okay, is the equivalence corresponding to the reference frequency. And we have 5 sources. They are uniformly distributed. Okay, 5 sources. So 3. So each subarray you only have 4 sensors, right? So it's underdetermined for each subarray. And then this DOA estimation results. So all 5 directions have been distinguished and identified successfully. Okay, and we calculate the RMSE versus SNR. So you can see with increase of this SNR, so you get a better result. And RMSE versus snapshots. Okay, similar trend. Okay. Now for the localization result, again, so same reference frequency, same frequency range of the interest, and so same sampling frequency, and the range is the same. But now we have 6 subarrays, okay, and with this corresponding rotation angles relative to the axis, and we employ the same 4 sensor MRA for each platform. Okay, and we have 5 sources. We have 5 sources located at this 5 okay, positions, okay. So because 5 will fall, so again, so underdetermined. And here is the localization results. So basically very close to the true target location. You compare this like this one, so minus 9.6, minus 13. I think is x minus 10. So basically this one corresponds to this target 1. So minus 10, minus 13, right? But here is not minus 10, it's minus 9.6, a little bit error. And this y is exactly, there's no error, okay? So you can compare these results with this. So you can say, okay, they have been identified correctly, okay? And then you have this RMSE versus SNR result, okay, from minus 5 dB to 20 dB. So you increase dB, increases SNR, so estimation error is decreasing accordingly, okay. For this RMMC versus number of snapshots, okay, again, you get this improvement with more and more snapshots available. So that's this section 6. So finally, so section 7 is a summary of this whole tutorial. So in this tutorial, introduction to wideband array signal processing, including beamforming and directional rival estimation was given first, highlighting the main differences compared to the narrowband case, okay? So I hope now you have been, you have known this difference, clear difference between narrowband beamforming and wideband beamforming, narrowband DOA estimation and wideband DOA estimation, okay? And then a review about sparsity-based underdetermined narrowband DOA estimation methods was provided as they form the basis for many wideband methods. And for underdetermined wideband DOA estimation, we have focused on 3 cases. So the first one is apply this group sparsity concept directly in the frequency domain. Either impinging wideband signals share the same set of spatial spot across the whole frequency band of interest. And instead of relying on the sparse array structure, this second case, so frequency diversity can be employed for underdetermined estimation, and even is a standard URA structure. Okay, so in the second case, we don't need to employ this sparse array, so we can just use a standard URA. We can still do this underdetermined DOA estimation. And in the third case, we have focused on this higher order statistics-based method, okay, using this cumulant in our simulations. And to reduce the complexity, we have applied focusing to this third case, okay. You can apply focusing to all wideband-based method, basically, okay. So in the last part, the target localization problem was studied, and a new group sparsity-based method was presented to find target location directly based on a system of multiple distributed sensor arrays. And then there's one topic we have not touched yet in this tutorial is what is this CRB, okay? The CRB derivation, okay? We haven't mentioned this. We didn't provide this CRB in the simulation results. But if you are interested in this, you can refer to these 2 references for this detailed derivation of CRBs for all cases, okay? And so far, we have also, okay, only assumed the signals, they are not correlated with each other when we generate the virtual coarrays, okay? If you don't need the coarray, then they can be correlated, no problem. But if you want to use the coarray concept, then they have to be assumed to be uncorrelated with each other. And if we know more about the signal spectrum, So if we know more, not just wideband, we also know the spectrum, the shape of the spectrum, then we could have even more degrees of freedom for more effective underdetermined wideband DOA estimation and target localization. This can be a direction of future research in this area. So with more and more information about the wideband signal and what we can do to achieve even better result. Okay, so that's all. And here is a list of references. So we have 49 provided 49 references. There's a lot more. I just you know, if you're interested, you can read the relevant papers. You will see more references in those papers. Okay, so that's all for this tutorial. Thank you for watching these 3 videos, and I will be there to answer any questions you have. Okay, thank you.